All right, so we're starting off in chapter 12, and I do expect you to read the sections of the textbook that we're studying, and probably helpful to do that before you go through the example problems for that section. So 12.1 is just an introduction. I still suggest that you read through it. In 12.2, we're introduced to some equations for continuous motion. This is the equation sheet that's on the M drive. So like I said in the last video, I would go ahead and print that off. Most of the equations come right from the textbook, and if there's a number with the equation, that is the number that it's given in the textbook. So there we go, there's equation 12-1. Now some of the equations don't have numbers because they don't have a number in the textbook. Some of the equations that have numbers in the textbook, either I didn't think they were important enough to be included on my equation sheet, or I didn't like the way the equation was written and I wanted to write it a different way. So let's see, the first two rows of the equations that we have here are going to be enough for section 12.2. And most of these equations we've seen before and we're very familiar with them, and I bet that if you try and do the first few fundamental problems in the textbook, you probably could do them right now without even watching the rest of this video. But some important things to note in this textbook, displacement is delta S. So if you use spiral physics for physics 161, we used an delta R for displacement instead of a delta S. So that's one difference that we have there. Okay, so this is figure 12-1, and this is part B of the figure, or let's go up to part A. Okay, so S is the position measured from the origin O that they have here. Then the point particle moves to a different position. That new position is, I don't know if you can see that, but if you take a look in your textbook, that would be S prime. So the difference between the final position and the new position, no, the final position and the initial position is delta S. Okay, and then, as we know from physics 161, if you take the derivative of position with respect to time, you get the velocity, and let's see, the average velocity they have here as the change in position over the change in time, which is included on our equation sheet also. And if you remember from physics 161, if the acceleration is constant, the average velocity is the same as the derivative of the position with respect to time. Okay, and the acceleration is the derivative of the velocity with respect to time. That's equation 12-2. Now this equation we didn't necessarily see in physics 161, but it comes from simply taking equation 12-1 and equation 12-2, rearranging them to solve for delta t, and then taking the ds over v, which you get from equation 12-1, and setting it equal to the dv over a, which you get from equation 12-2. And then you take this and you multiply both sides by v and a, and we get a ds is equal to v dv. Okay, so let's write that down here. So we have a ds is equal to v dv. Now, if we integrate that equation, which they do on page 8, this is the equation, it's going to give us equation 12-6. They integrate this, but when the acceleration is constant. When you do that, you get this equation here, which might look familiar from physics 161. Okay, so we're not necessarily familiar with equation 12-3, but we are familiar with what we get when we integrate this for constant acceleration. Okay, so one other thing I want to point out is if you take this equation here, no, that's not what I want to do. If you take the equation that you get after integrating, well actually we can go back to this equation here. We are going to have to integrate the right-hand side, but it will be fine. So I want to take this, and I'm going to multiply it by mass on both sides. So I have mass times acceleration, ds, is equal to mass times velocity, dv. I'm not going to integrate on the left-hand side, but I am going to say if I have mass and acceleration, we saw that is equal to the net force. So I'm going to call this the net force, and I'm going to make that a dot product, which it's supposed to be. It is supposed to be, but they don't say that in the equation sheet, but it actually should be a dot product, and I think we're going to talk about that later. I integrate that from, let's just say, S1 to S2. I don't know what the final position and the initial position are, so we'll just do that for now. On the other side, I can't actually do the integration because the mass, if it's a point particle, the mass isn't going to be changing because if the mass was going to change, the object would have a size and a shape then. So assuming it's a point particle, we can also assume that the mass is going to be staying the same throughout this. And then if you integrate v dv, no matter what's going on, you'd still get the same thing when you integrate. So that would be integrate v, and you get v squared over 2 from v1 to v2. So I'm going to pull out the 2 in the denominator and call that 1/2 times the mass, and then this would be v2 squared minus v1 squared, or you could write this as going from S1 to S2, F net dotted with ds, 1/2 mass v2 squared minus 1/2 mass v1 squared. But, as you may remember, 1/2 times the mass times the velocity squared is, that is our kinetic energy, which we're going to be using a T for in this course, but that's when we get to chapter 14. So for today, let's just call it KE2 minus KE1, or we could call that delta KE. Delta KE is equal to the work done, the total work done, which is also the work done by the net force. And let's see if they have this equation. Haha, here on the equation sheet, except we have a dr there for some reason instead of an s. They're not always very consistent with the letters that they use in this textbook. So here it's an r, here it's an s, but anyways, it is equal to the work. So our equation here is actually related to the work energy conservation law. I don't know what I want to call this. Because, well, I used a W for it here, but that's not what they use. We'll just call it the work. And that is the work done by the net force, so that would be the net work, or the work done by all the forces. Okay, so what we got from equation 12.3, and then back on the previous page we saw the average velocity is equal to the change in position over the change in time. And then we have this equation here, and this is the average speed, which, here we go. In figure 12-1, they show the object started here and the object ended here. But if you use the definition for average velocity, which I don't really know that it's not really that useful. They might ask you a question about it in the textbook just to make sure you understand it. But this is the displacement, which has to do with the initial point and the final point. But it doesn't matter the path that the object took to get from this point to this point. So if you do the average velocity, you just do the displacement divided by the time. But let's say this was your car, and you drove all the way over here and then turned around and came back, the average velocity is going to be smaller than the average speed. So the average velocity is the final position minus the initial position divided by delta t. Whereas the average speed is the total distance traveled, so the length of this path divided by delta t. Okay, so the S sub capital T that we have here is the length of the path. That is the total distance traveled. Okay, we talked about equation 12-2 and equation 12-3, and then on page 8, they integrate those equations with constant acceleration to get the next three equations that we have here. So this would be from equation 12-2, bringing the dt over to the other side and calling the acceleration constant. So the acceleration is equal to constant acceleration. That gives us this equation 12-4, which is one of our kinematic equations in Physics 161. So this is review from Physics 161, and I don't think I need to say that much more about it, but you should be reading the textbook to see exactly how this is done anyways. Okay, and then we have equation 12-1, which says velocity is the derivative of position with respect to time. And if you integrate that, you get another one of our kinematic equations from Physics 161. And then we talked about equation 12-6 already, but these three equations are only true when the acceleration is constant. So in Physics 161, in Model 3 and Model 4, the acceleration wasn't necessarily constant, but back in Models 1 and 2, those are the three equations that we were using. Okay, so on page 9, we have a blue box with important points and a green box with a procedure for analysis. Suggest paying careful attention to the blue box there, and also pay attention to the green box as well. But the blue box gives you a nice summary of what's going on. We have some example problems here. I do want you to read through the sections that we go over. I know other students have found the example problems helpful, so probably would be a good idea for you to go through them, but I don't necessarily need you to do that. Okay, so if you find them helpful, go ahead and go over them, but I'm not going to assume that you're doing that. Okay, so now let's go ahead and look at fundamental problem 12-1. Okay, so initially the car travels along a straight road with a speed of 35 meters per second. If the brakes are applied and the speed of the car is reduced to 10 meters per second in 15 seconds, determine the constant deceleration of the car. Okay, so let's write down what we have first, and I'm going to do this. Instead of using the book, I'm just going to use that, which has the same problems on it. Okay, I got my equation sheet here, and let's go ahead and do this on a new piece of paper. Okay, now I would like you to follow along with me. You should be taking notes during the lecture anyways, but especially when we get to the example problem, you should be writing this down. Okay, so we have fundamental problem 12-1. The car travels along a straight road with a speed of 35 meters per second. So that is the initial speed. Let's call that V1. And if you feel that you can do this problem on your own, you can go ahead and finish it, play the video at a faster speed, and just check your answer at the end. Okay, so if the brakes are applied and the speed of the car is reduced to 10 meters per second, so V2 is 10 meters per second in a time of 15 seconds, so that's going to be our change in time. Determine the constant deceleration of the car. Okay, so it's a constant deceleration, which means that, oh, I don't think I have this equation on my equation sheet. Oh, let me just take a look in the textbook and see if we have this here. Okay, well, this is the best I can do. They say that the average acceleration is the change in velocity over the change in time. But like I mentioned with the average velocity, with the average velocity, I said if the acceleration is constant, the average velocity is the same as the instantaneous velocity. And if the acceleration is constant, the average velocity must be the acceleration because the acceleration doesn't change. Okay, so we are going to say the acceleration is equal to the change in velocity over the change in time. Okay, we probably could have said that before we even started this course, but there you go. Change in velocity is v2 minus v1. Then we'll go ahead and v2 is 10 meters per second. v1 is 35 meters per second. This is divided by the change in time of 15 seconds. Go ahead and plug that into your calculator. I have already worked these solutions, so I'm not necessarily going to be plugging things into my calculator when I record these videos, and so I suggest that you pause the video and just double check to make sure that everything works out. And then check your answer. So for this, we will get minus 1.67 meters per second squared. And let's go ahead and box that because it's our final answer. Since this is a fundamental problem, if you were doing this on your own, you could check the solution in the back of the book. It is negative because we ended at a smaller speed, and that makes sense because they said determine the constant deceleration of the car. Because the velocity is positive and the acceleration is negative, this means the car is slowing down. Okay, well, that was so much fun. Let's go ahead and do fundamental problem 2. A ball is thrown vertically upward, there it is, with a speed of 15 meters per second. Determine the time of flight when it returns to its original position. Well, this is interesting. So we're given the initial speed. We want the time of flight. Okay, we're going to have to remember a few things from Physics 161. So when it returns to its original position, what is its velocity? So if you remember from Physics 161, the ball goes up, turns around, comes down, doesn't move to the right, but I draw it that way so all my arrows aren't on top of each other. And when it gets back to the same height, its velocity has the same magnitude, but the opposite direction. And so v2 is going to be, if the velocity was positive to begin with, it's going to be negative. When it comes back down, it's going to have the same magnitude. And what is the acceleration in this case? The acceleration is 9.8, and I think, let me see, I think in this textbook we're going to be using 9.81. Let me take a look. Okay, so in their solution they do use 9.81. That's not what I did when I calculated it, and I don't feel like it's necessary to go back and change it, but we should be using 9.81 meters per second squared. We're going to use the same equation that we used for fundamental problem 1. The acceleration is equal to the change in velocity divided by the change in time, but now we are solving for the change in time, so the change in time is equal to the change in velocity divided by the acceleration. The change in velocity is v2 minus v1, so that's minus 15 meters per second, and then you subtract v1. v2 is already negative, and then you subtract positive v1. And divide by the acceleration. The acceleration is negative because they said the ball is thrown vertically upward. So the ball is thrown upward and this velocity is positive. The acceleration is downward. So since it's pointing in the opposite direction of the velocity, it would be negative. Or you could reason that the sign's out this way, if you're looking for the change in time, it had better be positive, which means your denominator is going to need to be negative. I got 3.06 seconds for that, but I think I did that with a 9.8, so your answer might be slightly different. Okay, and that is fundamental problem 2, and we're going to stop here and do our next example problem in the next video.